The rodeo is an event as purely American as the cowboys who take part in it. Its origins go back to the early days of the cattle drives and stock roundups. Today, on any given weekend, summer or winter, you can be sure a rodeo is being held somewhere in these 50 states. You don't have to break your neck to please the rodeo crowd. An arm will do just fine. These scenes were filmed at the Texas State Fair in Dallas. Big-time rodeo stars are among the contestants here. As many as 500 cowboys enter the various events in hopes of earning enough prize money to put them on top of the Professional Rodeo Cowboys Association money list. At the end of the year, the contestant who has won the most money in any one event is given the title Champion Cowboy. You know, I've spent a good deal of time with cowboys and stunt riders on the sets of Western movies. Some of them came to Hollywood after giving the rodeo circuit a try. They were looking for a less dangerous way of making a living. That's right. Rodeo takes its toll in lives and crippling injuries each year. A contestant can be badly injured or worse while trying for a prize in bareback bronc riding or the classic saddle bronc. But the worst, the most dangerous, is bull riding. Yeah. Bulls are just plain mean. Yeah, they're born mean. And when you're sitting up there on top of 1,800 pounds of tightly packed sinew and muscle, you might say it's kind of like pumping an energized fluid into a treating line with all the valves closed. Something's got to give. That bull's going to try to get a horn into you. And if he can't do that, he'll try to step on you, to crush you with his 1,800 pounds. Not every cowboy enters the bull riding event, and with good reason. Those who do recognize the potential danger and take steps to cut down the risks as much as possible. How? By making sure a rodeo clown is in the arena to distract the bull when their ride is finished. How important is the clown? Let's ask a recent winner of the national finals, champion cowboy Denny Flynn.
The clown is very important. Most bulls will try to run over you or try to fight. It's just an instinct in them. If you buck off a bull, it's just in them to fight. If you're down on the ground, they'll just turn and come at you. To me, that's the most dangerous part about riding bulls, is getting up and getting away from them after you make the ride. There's no one out there to help you other than the clowns. You can't turn your back on a bull. The danger isn't over until the bull is back in the pen.
It's the same with you Dowellers when servicing a well with an energized fluid. The potential danger from working with these materials isn't over until the last of the iron has been racked up and you're on your way back to the district. Until then, remember, a bull rider can be shaken up, even knocked unconscious, and still escape because he has a clown helping him. Now, at a well site, it's up to you. Out there are no clowns. A bull is harmless when he's properly restrained in a pen or chute. So are nitrogen and CO2 if handled with care and safety. But open the chute and an enormous amount of energy is suddenly released. It's the same with energized fluids. That's why we use them so effectively downhole. But if liquid CO2 becomes trapped in an enclosed area, say a 4-inch pipe used in treating oil and natural gas wells, and the temperature of the air warms it, can be as dangerous as any bull. As the temperature continues to rise, the pressure of that liquid CO2 will increase and try to burst out of the weakest point in the line. Now, when this happens, it's like the bull being released from the chute. Shrapnel-like pieces of metal will fly through the air with the force of a bullet. At the same moment, the rest of the line will whip around like a striking rattlesnake. If you're in the way, you'll be hurt. It's happened before. Too many Dowellers have been seriously injured, even killed, by a treating line failing under the pressure of an energized fluid. Did you ever see an animal trap sprung It's the same principle. The sudden release of tightly concentrated or compressed energy. Now, the recoil of a rifle or a shotgun is another, as is the sudden thrust of energy from a rocket motor at ignition, or the blast caused by the release of energy in explosive materials. Now, some of you Dowellers must be wondering, how is it that such useful tools as nitrogen and CO2 can turn into raging bulls? What causes this to happen? Well, we've asked an expert, Dowell's business manager for stimulation services, Jim Harmon, to answer that one for us.
Thanks, Glenn. As long as CO2 is moving inside of a pipe that's been properly hooked up according to Dowell safety and loss prevention standards, we really don't have too much problem. It's when it stops moving that we can begin to get into trouble. I think I can demonstrate to you on this chart that I have plotted here what can happen. On the bottom, I have time plotted in minutes, and over here, I have change in temperature in degrees Fahrenheit. Let's take a day where the temperature is 60 degrees. Now, let's say the job is down for 10 minutes. The CO2 is not moving. It begins to take on heat from the atmosphere. If we draw a line from 10 minutes up to the curve and then over here to the change in temperature, you can see that we have gained 30 degrees. The increase in temperature is making the CO2 expand. It's inside the pipe. It has nowhere to go. So the expansion causes the pressure inside the pipe to build up. In this same 10 minutes, with a 30-degree change in the temperature of the CO2, the pressure inside that pipe will increase by approximately 3,000 psi. And if the pipe is not designed to stand that pressure, you know and I know what's going to happen. The pipe will burst, and that's when we have got big troubles. What causes the pressure to be trapped inside of that pipe? I think if you'll follow me over here to this set of drawings, I can demonstrate what I've drawn here is a representation of the suction side of a CO2 hookup job. If you imagine a transport over here and the CO2 booster pump over here, I think we can demonstrate how liquid CO2 can get trapped inside of this line. The first example is that if we have the valve closed here and a valve closed here, then the whole pipe is full of liquid CO2. Now, according to the Dowell safety and loss prevention standards, we must always have one of these valves open, never two of them closed at the same time. Another condition that can cause liquid CO2 to be trapped inside of this line is that if we have the bleed-off improperly placed in the line, it must be at all times at the lowest possible point in that line. In this example here, you can see that the bleed-off is above this part of the line. If we bleed off the CO2, it will recede to this level, and when this kind of condition exists, then ice begins to form along this interface here, all along here. We now have an ice plug formed right here in this pipe, restraining the CO2 from going in this direction. And over here with the transport, if this valve happens to be closed, then the CO2 has no place to go. And if you remember, the 10-minute interval increases the temperature by 30 degrees Fahrenheit, and that results in an increase in pressure of approximately 3,000 psi. And if this pipe is not designed to withstand that pressure, it will explode and fly off in all directions.
Jim's example shows what can happen when the atmospheric temperature is 60 degrees. Now, if the air is warmer, the pressure inside the line will build up even faster. Now, what exactly can happen when an energized fluid is not properly handled? Handled as prescribed in the Dowell safety and loss prevention standards? Well, we're going to show you. Here at Dowell's Training Center in Kellyville, this treating line has been deliberately weakened at a predetermined point so as to simulate a line failure with an energized fluid. We are also going to show you what can happen to an unstaked and unchained flowback line. In charge of these controlled safety demonstrations is Jim Ritter of Dowell's Mechanical Research and Development Department.
What we're doing today is simulating two events that can happen to us when we're pumping an energized fluid. One of which is to lose control of a flowback line, and the other of which is to have a massive failure in a normal treating iron situation.
First, the flowback, unstaked and unchained, without a choke nipple and double valves that are required for this operation. On an actual job, the line failure we're going to see could happen only if there were a violation of procedure as defined in Dowell's location standards 5, 9, and 11. Mannequins are placed near the flowback line. Now let's see what happens.
Look at this. This one must have been hit by the stake at the wellhead.
The best way to prevent an accident when handling energized fluids is to review Dowell safety and loss prevention standards before you go on a job. You've got to handle it right, you've got to restrain it, and you've got to do it by the book. Because if you don't, then you will be caught on the horns of a mad bull.
The other thing we're going to do today is simulate the massive failure of a Dowell treating iron using gasified fluids. The way we're going to do this, and we're doing it primarily to find the safest way to do it, is that we have built in some weak points into the system that will enable us to predetermine where the system is going to fail. The system should fail in this particular instance at around 8,000 psi, and normally your treating iron is good to 15.
First, let's take a look at what happens when there's a break in a treating line, when we're pumping plain water. This time in slow motion. Hazardous, yes, but with this small volume in surface pipe, not likely to harm you unless you stood dangerously close to the line. But remember, that was plain water. So for the main event, the intentional bursting of a treating line, deliberately weakened at a predetermined point. But this time, remember, we're going to be pumping in energized fluid. Mannequins are positioned near this point to show what might happen on a job where we did not follow 5, 9, and 11, and a similar line failure resulted. In Dowell, this could only happen on a sloppy job, a job not up to standards. Inside the treating line, as the pumper steadily increases the line pressure, the nitrogen is fighting hard to get out. Any second now. And that was it. Exactly as the Dowell experts had predicted. The weakest part of the line failed at just over 8,000 psi. Let's take another look. This time in slow motion. Energy suddenly released. This will give you an idea of its powerful force. The full impact was felt by the mannequins. This 250-pound joint was blown 200 yards from the wellhead. Now, what you've just seen was what experienced Dowellers would call a sloppy job. Now, this one was done intentionally, conducted and controlled under the right safety conditions. Now, it could never happen on location unless a very sloppy job was done on a customer's well. Now, you know, nitrogen and CO2 are used safely by Dowellers on customers' jobs every day of the year. And yet, in spite of all the information we have about pumping energized fluids, information in the standards 5, 9, and 11, there have been accidents. Tom Branham of Dowell's Prestonsburg district was seriously injured, as was Hal Hedrick of the Artesia district. They were both fortunate. They lived. What happened? Well, Tom Branham, a service supervisor, had just bled the line off, but, well, let's have Tom tell us.
On our frac jobs using energized fluids, we were on a job out of Prestonsburg, Kentucky, and then to Virginia. The job was completed. We were trying to get the pressure for the customers. In this instance, the line parted. And at this point, I have no idea as to what happened to me. No recall as to ever. Since that time, I've been on foam jobs and nitrogen jobs using for return purposes only, an energized fluid. Been on CO2 jobs. We've got to have respect for these fluids. By using our standards 5, 9, and 11, we should be able to safely do these jobs, and that is the only way we can do it, is safely.
Tom was hit by a treating line. It broke his collarbone and 4 ribs. Hal Hedrick, also a service supervisor, was hurt when a valve bar he was using struck him, badly damaging ligaments in his knee.
I'm Hal Hedrick from Artesia, New Mexico, and last year while on a nitrogen acid job, we balled out to approximately 6,500 pounds. I went up and I was a little bit too anxious to get the pressure off, and I was bleeding it back and the line separated. I got a little bit too anxious in blowing down the well.
No matter how many times you may work with energized fluids, no matter how well you think you know how to handle these wild bulls, you must never let your guard down. Denny Flynn, the champion bull rider, let his guard down once and almost paid for it with his life.
Was on a bull that didn't particularly want to get on because his horns were pointed upward and they were sharp. And I'd been traveling along for 23 days in a row. When I was getting off, I just kind of loosened up and was going to jump off, and he just scooted out in front and throwed me back on his hips and then just kicked me up in the air. And I came down, he ran a horn through my stomach, went up 10 inches, right up through my rib cage, and I was real lucky. It didn't tear up anything, split my liver. I was just real lucky.
Johnny Huckabee, service supervisor of Dowell's Graham district, he wasn't so lucky. Johnny lost his life when a 4-inch chicksen burst during a CO2 job. Now, after this happened, a team of Dowell and other Dow engineers, metallurgists and specialists in other areas, conducted a thorough investigation of this tragic accident. Now, the information they gathered was compiled and studied in order to prevent a like accident from ever happening again. CO2 and nitrogen jobs are potentially dangerous. You see, potentially, that's the key word. But if handled correctly, these jobs are as safe as any other. So let's go out and see one, huh? Billy Wood of the Artesia, New Mexico district is in charge of this acid job using CO2. And now let's meet Service Supervisor Charlie Rawson. Let's hear how he feels about working with energized fluids.
I feel very comfortable working with energized fluids. I've worked with energized fluids out of the Hobbs district for a number of years. we've had very good success and no unsafe jobs handling CO2 or nitrogen with Dowell people and equipment. Once you get on location, your hookup should be in a safe manner. In order for this to be in a safe manner, each and every employee should know the standards 5, 9, and 11. And after this has been gone over, we're in a group meeting with a pre-job meeting, then proceed with the hookup in a safe manner with the instructions, with the proper equipment, and the tools given to you. Then you can do a good, safe job using nitrogen or CO2.
And that seems to be the consensus. You must know safety and loss prevention standards 5, 9, and 11 before setting out on a job using energized fluids. If you don't, you're like a contestant in a rodeo riding a wild bull without a clown in the arena to distract him when the ride is over. In other words, you'll be putting your life on the line because the only way you can handle that wild bull safely is by doing the job and every phase of it correctly. And that means by the book. It takes knowledge to work with energized fluids safely, and the more you know about the subject, the safer you're going to be. Remember, out there on that location, a mistake can be fatal. Out there are no clowns.